Hello guys. Okay, today I'm gonna solve an example, and this example is gonna be I'm going to do a beam once again. The beam is gonna have a fixed support here and a roller on the tip. And also it will have a hinge, a distributed load here, rectangular, and an internal hinge. Also, I'm going to put a vertical load and a concentrated moment at this end. Concentrated moment 800 pounds per foot. Distributed load 150 pounds per foot. I say pounds per foot here, it's not pounds per foot, it's pounds foot. This load is 700 pounds. The distances are 8 feet, 4 and 6 feet. Okay, let's name this. This is named as A, B, C, and I'm going to put a D here also. Okay, the first thing that we have to do when we have this type of problems is verify if this structure is statically determinate or statically indeterminate. And how do you do that? Well, you have to remember the number of reactions. First of all, this is a fixed support, meaning we're going to have a Y, AX, and MA. And here is a roller, so we are going to have only one reaction normal, CY. So I have 4 reactions total. And if you remember, reactions has to be equal to 3 times N. So we have 1, 2, 3, 4. And these two also, I have to count them because even though they are internal for this method, I have to count them. So I have 1, 2, 3, 4, and 2 for the internal hinge are 6. 6 reactions has to be equal to 3 times the number of elements, and I have 1 element and 2 elements. So 6 equals 6. That means that is statically determinate. So we can continue solving the problem. Now, how do we solve this problem? We take advantage of the fact that I have a hinge here, and you know that if you make a section anywhere in this beam, when you make a section, we have studied that sufficiently. When you make a section anywhere in that beam, you are going to have always shear, action, and moment. But the problem is, the fact is that when you start doing that and you are dealing with a hinge, basically what we are doing here is we are saying, oh, if I do the cut at the hinge right here, and I study this part, I know this is going to be here, and I know this is going to be here also. And because this is a hinge, I know for sure that we will have this shear. And remember, we are using this side. That's why the convention, I'm putting the convention in this way. And we are going to have also a moment in this end, like that. And we're going to have an axial force. But because this is a hinge, I know the hinge cannot support any type of moment, withstand any type of moment. So this moment is going to be 0. The axial is 0, but for different reasons. The axial is 0 because I don't have any axial force. So this is 0 because of that. But the moment is 0 only because of the reason that this is a hinge. And the hinges are designed in such a way that they don't withstand moment. Remember, if you have a hinge, it's free to rotate. If it's free to rotate, it's not providing any moment. And because of that, then I can solve, because I only have these two unknowns in my system. So this distance is 6, and this is 150 pounds, which produces a concentrated, it doesn't produce a concentrated, we transform it for our benefit, for our convenience, in a concentrated force of 900, and at the distance of 3 with respect to any n, because it's at the center of the load. So then we can start doing this, and we can say summation of moments at B equals 0. And if I do that, and I apply moment here, then we're going to have this force, which is negative 150 times 6, or negative 900, times the distance from here is 3. Why negative? Remember, because it's rotating in this way. Plus this force, Cy times 6, and I have a negative moment of 800 here, also equals 0. And look, the only unknown now is Cy, and I can solve for Cy, and Cy is 583.3 pounds. Now, I can put everything together. By the way, we don't need this value here, because I'm calculating external reactions, but let's calculate it just for fun. So if I do that, I can do summation of forces in Y equals 0, and then I can say that VB minus 900 plus Cy, which is 583.3 equals 0, and my shear then at that point is going to be the difference between these two. The difference between these two, let me see if I have the value here. Yeah, it's 316.6 pounds. That's going to be the value of the shear at the hinge, which I don't need for my external reactions anyway. Okay, now once I have that, I put everything back together, and then I can do summation of moments in my whole beam here, and I have 1 and 2 unknowns, because this AX is also 0. So I have 1 and 2 unknowns, and the only unknown that I have is the moment here and Cy by doing that. So I can do summation of, I'm going to use a new piece of paper for that. I can do summation of moments at A equals 0, and if you do that, then in this direction positive, you have MA minus 700 times 8. Remember, I say minus because the rotation is going to happen in this direction. Now, remember we converted this. Now, when this is together, this is not separate. The internal reaction is just that, an internal force. So it doesn't show. But the external force here, yes, it does show. And this value we calculated before, it was 900. And we say that the distance here was 3. So then is MA negative 700, and then I have this force here of 900 times the distance from here to here, which is 8 plus 4 plus 3. 8 plus 4, 12, plus 3, 15. Now Cy positive, and Cy we calculated as 583.3. Remember, this is periodic. I want you to put all the decimals in that. Times the distance from here to here, the distance is 8 plus 4, 12, plus 6, 18, minus the moment, equal to 0. I don't have anything else. And from here you can solve for MA, and MA is 9,400 pounds per foot. And once I have that, I can go and solve, or before I could do it also, I can solve for summation of forces in Y equals 0, and I can use the whole beam. So I'm going to have AY minus 700 minus 900 plus the value of Cy, which we calculated as 583.3 periodic, and in that way we can solve for AY, and AY is going to be equal to 1016.6 pounds. Okay, now after you have the reactions, what I will say is verify your reactions, just for the sake of knowing that what you're doing is correct. So I can take maybe summation of moments at B, because if I do summation of moments at B, I'm not eliminating any of the forces. Summation of moments at B equals 0. Remember, this is just for verification purposes. So if I do that, then we will have AY, which is 1016.6 times 12, and it's coming in this direction, negative, plus MA, which is 9,400, plus 700 times plus 4. Now go to this side, 900 times 3, and remember it's negative because it's acting in this way, plus CY, and CY is 583.3, positive, times the distance from here to here, which is 6, and then I have negative 800 equals 0. And here you're going to demonstrate that 0 equals 0. And the meaning of that is that our reactions are correct. That's it. Now, once we have that, we can start the process of solving or drawing the shear moment diagram. How do we do that? Well, remember, we have to put a line at the beginning and a line at the end. And then we have to put intermediate lines in everything that I called points of interest. What are those points of interest? Wherever you have a concentrated load, whatever you have a force that begins, a force that ends, a concentrated moment. So basically, this is what we have for this case. Now, I'm going to solve this by using the method of the areas. Remember, we're going to need one line for the shear, which is going to be in pounds, and another line for the moment, which is going to be in pounds per foot. And let's solve this. First thing first, I like to. It's not a requirement, but I really like to. I find it highly beneficial to get the values of my reactions and put the values of my reaction wherever they belong to. So this value is 1016.6 periodic. X, I didn't do it, summation of forces in X, but it's 0. Because if you do summation of forces in X equals 0, AX is 0. There's nothing else working or going on in X direction. And this CY is 583.3 periodic here. So then we start, and we start from the point we start from the point A, and you say point A. Do I have any concentrated force at the point A? Yes, you can bet that we have. We have a concentrated force going up, and the value is 1016.6. That means that's going to be the value of my shear. So I go up at that value, 1016.6. Now we go to the span AD. Remember, we're doing shear first. Span AD. And if you look at the span AD, it's supposed to be this value plus the area of the load on top of this section, but there's no load. So there's no load. That means that my value is going to be constant. 116.6 pounds. So from here to here, it's going to keep constant, that value, 116.6. And now we go to the point D. Do I have any concentrated load? Yes, at the point B? Yes, we do have. So what I have is 1016.6 periodic, and then I have this load coming in this direction of negative 700. That's the concentrated load, and the value is going to be 316.6. That means that from this point it's going to be a jump up to negative 316.6. Now we go to dB, and we say the result here is going to be this negative so we go to the point D, and we ask the question, do I have any concentrated load acting down? Yes, of course I have. And then what I have is that at this point I have 1016.6, and I found this force of negative 100, which is going to push it down up to positive 316.6. From here, in the same direction, it's going to reach this value here, which is 316.6 periodic also. And now we go to dB, and we say, do I have at dB any load? I don't have any load here. That means that no load, constant value of 316.6. So that means this value is going to stay constant up to that point, 316.6. 316.6. That's the value of the shear over there. Okay, now I go to the point B. Do I have to do anything at the point B? No, not really. But you remember that I told you before that just for fun, I was going to be calculating this reaction here just for fun. Look at the value of the shear at the point B, which is the hinge, 316.6 pounds. Look at the value that we got at that point from the diagram, 316.6 pounds. That means that we are working correctly. If by any chance you got a value here differently than the one that you calculated before, that means that you mess up the calculation somewhere. Okay, now we go to the point B. Do I have any concentrated force? Point B. No concentrated force, no change. And then we go to BC. So when you go to BC, then you have this force and you have this value. Originally I have 316.6, and then I find this, which is negative, by the way, because the arrows are coming in this direction. So I'm going to put it as negative. I can put plus a negative area, but it's the same. And this is 150, and the base is 6. Which, when I do that, is like saying 316.6 minus 900, and that's 583.3, and this value is going to be negative. So from this point, I'm going to reach up to negative 583.3. This is going to be a straight line, and then you say that this is a negative slope, and once you reach this value here, you go to the point C, and you say, do I have any concentrated force? Well, I was coming with negative 583.3, and then I found this force, which is the reaction at that point, the reaction at this point, 583 going up, and that's going to give you 0, and that's your first yes. And this will go here and ends in 0. There you go. Shear diagram done. Now let's go for the moment diagram. For the moment diagram, we start at the point A. And at the point A, Okay, at the point A, then we see and we ask the question, moment. Do I have any concentrated moment acting at the point A? Well, you have this concentrated moment at the point A in this direction, like that, and this direction. And if you remember, we say that whenever you have concentrated moment, everything that is acting in this way is positive, and everything that is acting in this way is going to be negative. So our moment is acting in this way, like that, which is negative for our purposes of plotting the values. This is going to be negative, this is going to be positive. What is it? No, this is not positive. This is... Okay, for the moment, the first thing that we do is go into the point A, moment. And if you remember for the moment, then we said that this is going to be positive and this is going to be negative. In our case, the first moment that I found is coming in this direction, which is negative, according to this, and this is going to be 9400. Negative. It's a jump in this way. I have a moment of 9400 in that way. Okay? Now, we continue for AB. AD. And AD, we found that moment, which is negative 9400, plus this area. And that area is 1016.6, and this is 8 feet. When you calculate that, that's going to be negative 1266.6. So from here, I'm going to reach up to this point, which is negative 1266.6. And because this is constant, this is going to be also a straight line, constant. Positive slope, because this is positive area. Okay, now, keep going. At the point D, no concentrated moment, no change at that point. And then we go to DB, and DB, I have to get this value, which is negative 1266.6, and I have to add this little area, which is a positive area. This is 316.6, and this is 4. When I add this, I'm going to get 0. Remember, this is 4 times 316.6. 0, a moment of 0, meaning that exactly at this point, which is the hinge, whatever the hinge is, I'm getting 0, which is the value that I'm supposed to get. And that's another way of verifying what we are doing is correct. Now we go to this part, and as you know, this is a very interesting point here. Look, even if you don't know what the value is here, just by looking at that shape, you can say, okay, we are working with, let's say, BB prime. Yeah, let's call this point B prime. And of course, I have to calculate this point. But let's say that you don't have time. And then I say B prime. And BB prime, this area is positive. And it's positive. Remember the circle? Please don't neglect infants, neglect dumb people instead. So this is positive because it's positive, it's plotted above the axis, and it's decreasing because the height of the shape is decreasing. Positive decreasing is something like that here. That means that my shape is going to be like that. That means that this value has to come up to this point. And then this is negative, right? And this is going to be negative increasing because the shape is increasing. And that will be B prime C. It's negative increasing. So I know that negative increasing is this, and that negative increasing is going to be like that. But this is not going to reach 0 here. Why not? Because I have this concentrated moment. And now if you look at that concentrated moment, that means that that moment is going to be positive. That means it's going to jump from here somewhere, which is the value of 800 is the one that is going to make it close. When I found this, it has to go here up to 0 because this is positive. So it has to be a negative 800 before, and I know this is going to be negative increasing, so this should go in this way, even if you don't know that point, if you don't have time. But we're going to do it as we did it before. So if I'm going to do it like that, I have to calculate this x value here, and we can say that for that x, you can say, okay, 316.6 is up to x, as 583.3 is up to 6 minus x. Or I can say also that 316 plus 583.3, so 900 is up to x, as 316.6 is up to, 900 is up to 6, I'm sorry, because it's the total length, as 316 is up to x, and solve for x, and x is going to be 2.11, so that means the value here is 2.11, and if you want, then you can get this 0 and add this value. It will be for that BB prime that we were doing before, it will be 0 plus 2.11 times 316.6 divided by 2, because remember this is this area, and that value will be 334, give or take. And then for the B prime, C prime, I will say that this is 334 minus, because this is a negative area, 6 minus 2.11 times 583.3 divided by 2, and that's going to be negative 800, which is this value here. And then at the point C, we have that value of negative 800, and then we find this moment of 800, which is positive, and that's going to be 0, and that's what is going to bring this up to 0, and then you can do and say your reserved yes. Okay guys, I hope that you like this problem. Please try to go over it and try to solve it in detail, and I'll see you later in another recording. Have a good day.